Hi, welcome. We're going to give it a minute or so for people to join in, and then we'll get started. Okay, we'll go ahead and get started now. Hi, everyone. Welcome to this Tecton webinar. My name is Julia Briette. I'm a product marketing manager here at Tecton, and it's my pleasure to introduce our speaker, Tim Hopper, a senior staff software engineer on the machine learning platform team at Varo Bank. Tim brings over a decade of experience working with Python and machine learning across a variety of fields, including cybersecurity, weather forecasting, public health, and now fintech. At Varo, he's at the forefront of developing cutting-edge ML systems for business-critical use cases like fraud detection, risk mitigation, and lending. He's also an incredible thought leader in implementing engineering best practices for ML and AI. And so we're very excited to have him share some of those with us today as he talks about Varo's approach to scaling AI innovation. So without further ado, welcome, Tim, and the virtual floor is yours.
Thank you very much, Julia. Get my screen share going here. Thank you all for being here. It's my privilege to talk about some of the work that we've done on our machine learning platform team at Varo Bank in recent years. This talk is entitled "How to Use Streaming Machine Learning for Real-Time Data," and we're going to talk about our machine learning platform, especially the data side of the machine learning platform, and then also how we've been able to use that beyond just machine learning purposes. I imagine not everyone's heard about Varo Bank. Who are we? We are the first nationally chartered consumer tech bank in the United States. So we are what I like to call a real bank, the bank charter backed by the FDIC, but not one of the legacy banks, but built on modern technology and for modern users. Built from the ground up to focus on the needs of Americans who are striving to get ahead, combining the agility of a technology company with the security of a regulated financial institution. You can see here some of our recognition that we've received, and you can learn more about us at varomoney.com, and even sign up for a bank account if you're interested, or maybe if you find my talk here compelling. Some of our distinctives at Varo, we have the opportunity to build credit with the Varo Believe secured card. We have high yield savings account with one of the nation's highest APYs, and we have faster payments using Varo Advance to stretch dollars between your paychecks. One of the goals of Varo is to particularly help Americans who are living paycheck to paycheck and help them build their credit, build their payments, and make faster, or build their savings and make faster payments. So my focus, I'm on the machine learning platform team. We provide all the machine learning infrastructure, tooling, data, everything necessary for our data scientists to be able to ship machine learning models that support all these banking efforts. Machine learning has a huge breadth at Varo. In the lending space, we have questions around should we provide a cash advance to a customer. In the risk space, we have questions around things like What's the risk that a potential customer is a money launderer, which the government is very concerned about and puts it upon banks to keep an eye on. In the fraud detection space, you can imagine the obvious banking concerns of fraudulent transactions, people with fraudulent uses of cards, things like that. In the marketing space, we have questions around who do we want to target with Google Ads as we seek to grow our bank and our customer base. In the product space, we have things, among other things, around like transaction labeling. So, for example, knowing if a particular transaction is a direct deposit transaction or not, and which allows us to take certain actions off of that. In our operations space, as everyone else in the world, we're currently investigating chatbots and a RAG assistant for our operations staff to help them answer and help serve customer questions. So these are the machine learning uses, potential machine learning uses, but all of these machine learning uses fundamentally depend on having data available to us. Machine learning, for the most part, doesn't happen without data. There's been a lot of studies showing that the best way to improve machine learning is often better data or better or more data versus better models. So data serves as just a fundamental underpinning for all of our machine learning applications. So that's my main role at Varo, is making this data accessible and available to our data scientists when they need it, where they need it, in the shape and form that they need it. So to further that point, machine learning specifically depends on what we call features. I imagine most people here are familiar with the term feature in the machine learning space. This is different from what we talk about feature in a normal software development environment. In software development, we think about a feature as a distinguishing characteristic of a software item, something like performance or functionality improvement, some component of the actual software. But in machine learning, a feature is just a data point that's used to serve as an input to a model in order to generate a prediction or train the model. So without these features, we don't have machine learning. Here are some example features you might envision a bank could have. The number of days since the last point of sale transaction on the customer's card, the average account balance to date for a customer, or you could think about like a rolling window, average balance over the last 90 days, something to that effect. The standard deviation of the account balance, how much is their balance changing, their average direct deposit amount, or maybe the customer's occupation. And from there, you could envision more and more possibilities of features that you could create based on banking data. And those features are things that could go into models and then perhaps make predictions, like the use cases we talked about above. Can we feed all these things into a model and then help quantify the risk of lending a cash advance to this customer, for example? So these features come from data. So feature generation, at the end of the day, is really largely an ETL process. And the same as other data transformation, data loading, we define the transformation that we want to make. We extract the data from some other source, and then we load that data into what has become popular in the recent years. It's called a feature store or a feature platform, a place where those features become available to our users. So this is different from often when I got into data science and machine learning 10 or 12 years ago, there was a lot of ad hoc approaches to getting features for any given model in a company. Each model maybe did that differently. They collected data from a data warehouse or from static files or from various sources, production databases potentially, and use that to train the models, and then maybe even use data from a different source to serve the models in production and perform what we call model inference. These days, companies have moved towards trying to standardize where that data becomes available in a feature store and make that data the same data, or at least the same shape and type of data available for training your models as you're also using in your model inference. So that's what we call a feature platform. From Varo, our features are generated from our underlying data infrastructure. So this is the infrastructure and data that's provided by our data engineering team within the company. The data in batch form is generated from our various internal services, which write to Postgres databases that are used. Those are production Postgres databases used for those services. And then that data is, as changes are made, that data is what we call CDC'd into Airflow, change data captured. So the changes in the databases are copied over into our data lake. And that data, those changes in the production data become the underlying data sources that are accessible to us for generating the machine learning features. And in our infrastructure, we're on AWS, and our data lake is accessible through AWS Athena or Spark via like a Hive metastore that makes that data available to various like Hadoop type services. Our data is loaded typically on a daily cadence, and then when that data is available in our data lake, it's available for us to generate machine learning features from. We also have streaming data available to us, so data in Kafka queues. Those same internal services write to these databases, and that change data for certain services is also written into Kafka using Debezium, and then other services are able to listen to that change data. So the big advantage here is that the data is, we don't have to wait for this daily batch job for the data to be copied into the data lake. The data becomes immediately available to us in the Kafka queue. So our feature store, which I guess isn't a secret, maybe which is built on the Tekton product, depends on these underlying data sources. We have batch data sources available, essentially through, you can think about just SQL access or Spark access. And then we have streaming data, which typically is available through some kind of Kafka interface where you deserialize these messages in the Kafka queue, and then you make some action on them. What Tekton provides for us and what our feature store is able to provide is a SQL interface that allows us to define machine learning features using the same type of query language that's been used for, I guess, generations at this point. And Tekton also provides a unified platform for batch and streaming data within offline and online retrieval. And that last part is hugely significant, and we'll jump into that a little bit deeper to talk about what that means. But for the end user, and our base of end users continues to grow at the company, we're able to define machine learning features basically as simply as writing a SQL query to define that transformation on the batch or streaming data. And as we transform the batch or streaming data, we are then able to write that out to our offline feature store, which is a place where we're able to query batch data for model training or batch inference, or our online store, which we're able to use to make real-time machine learning decisions. And as we'll talk about later, we've also extended that to other use cases even besides machine learning. So this unified platform has been one of the biggest benefits for us of using the Tekton platform, just immensely beneficial in the way that it unites data from two sources that while related, are technologically kind of miles apart, and it brings them together in a very familiar and friendly way, which is just hugely powerful. So the offline feature store, I already alluded to that. As we pull in data for each, as we define our features for each entity, which might be something like a user or an account or something to that effect, what would the offline store says, what would be the value of the features at time X in the past? And this is the data that we're able to use for training or batch inference. So as you think about training a machine learning model, often what you're wanting to do is taking historical data, how can I predict things that happen in the future? And so with the Tekton offline feature store, you're able to say, okay, here are all these users that I have, and at some point in the past, they, for example, committed, they had some kind of fraudulent transaction. Can I take that information to construct a model that's able to look for users now that are potentially committing a fraudulent transaction? So I can go into my feature store through the Python API and say, here are all these users in the past, and at this time in the past, they committed a fraudulent transaction. Basically, give me the state of that user via their features that would have existed at the time they committed that fraudulent transaction. And this is what we call time travel or a point-in-time join to collect that data. So as we're able to collect that, we can then feed that into a machine learning model, something like a regression or a random forest or a neural network, some other model, and build the ability to predict the fraudulent behavior. And then in the present time, as we want to use that model, we're able to use this exact same API to do what we call batch inference. So we say, for all of my users right now, give me the state of their features as of yesterday, basically, and use that to predict whether or not that user is committing some kind of fraudulent behavior, as an example. So we go from what I described in the past, where people often may have had some different ad hoc processes to collect this data at training time, and then maybe a different process to collect this data at inference time, to a unified path in your code to make sure that you're doing your feature transformations exactly right, your data cleaning exactly right, scaling exactly right. Everything is being done consistently from the model training as it is into the model inference, which in hindsight seems obvious, but hasn't always been the way it's done. And Tekton and other feature platform tools have really enabled that to make that easy for companies. Can't remember if I have a slide on this upcoming, but another really neat aspect as we talk about this unification is it's easy to just think about offline data and or batch data and then this offline store, but Tekton, as it provides this unification between batch and streaming data, you can send data from the streaming sources into the offline store and from the batch sources into the online store, which is really neat. So the online store, just mentioned, what does that provide? For a given entity, such as a user, an account, something to that effect, what is the current value of the features? And then this is something that we want to use for real-time inference. So there are kind of two different main dimensions here, why this is valuable for real-time. One, the way you retrieve the data is typically going to be on a single entity basis, and it's going to be much faster than what we're able to do with the batch feature retrieval. And then the other dimension is if you're using a streaming data source, perhaps that data can become available to you before the data from a batch or batch data source. So the actual request to get the data is faster, but then also the ability to update this data in the online feature store is faster. So an example of this is, somebody swipes their debit card, and then we need to do some sort of validation, perhaps looking for fraud or something similar on that debit card swipe, and that needs to happen instantaneously. Can we get data describing that user and up-to-date data, within milliseconds to make some decision that we need to make? And the offline store, the online store provides that. And again, this is part of the Tecton overall package and the offering that they provide to you that we use. With that, you're getting this data quickly, but again, as I was describing with the kind of batch training to batch inference, providing the consistency, we have that exact same consistency here between, even though this model is being scored online, it's typically being trained offline or in a batch fashion. So we train the model all at once, and then we run it in this online or real-time way. What Tecton provides for us is this ability to consistently generate that data for training and then generate this data for inference in a way that we don't have to worry that there's something fishy going on, and all those things I mentioned previously. Your data scaling, your data cleaning, processing, the way the data is acquired, it's all done consistently, so that the models don't get skewed because we're doing something different at production time from what we were doing at model training time. All right, so our feature store then provides overall this online and offline store. So this is, I think this is our internal diagram, but based on a diagram that we had from Tecton. In the middle of this, you have this online and offline store. Those are both populated through data transformations, which you see to the left. Those transformations are defined in SQL, and being able to load data from the data lake or from the Kafka data streams into the online and offline stores. There's also the ability, and I'm not going to go into this today, but to specify basically data in real time. So if you're doing these online this online inference or real-time inference, sometimes there's data that isn't available to you until the time of the transaction or the time of the inference. So for example, in a transaction, maybe you collect some data from the actual debit card swipe information and you feed that into it as well. The platform also provides, as you see at the top and bottom, data quality checking. Not going to delve into that today, but through Tecton and through internal tooling, we're able to validate and make sure that the data looks the way it should. We have monitor, logging, and alerting, so that if the data is failing to be populated, for example, we get an alert for the person on call to go and investigate that. Tecton, one of its most beneficial features is it provides a feature registry that's auto-generated from all these data transformations defined in the SQL, so that anyone in the company can go into the feature registry and see what types of features that we've had developed. And for our data scientists in particular, they can go and look, has a feature already been developed, so I don't need to redevelop this for my model. Then that data is served out through the SDK, which is the Python SDK to serve batch data, or through this online feature service where you're able to make basically a REST call and get immediately up-to-date features for a given user. And then that data can be used in model training, model serving, as well as some other applications like a rules engine, which we're going to talk about in a moment. So this feature store is really the backbone for the machine learning lifecycle. I emphasize this at the beginning, but and I guess I'm biased since this is my main responsibility at the job, but this underpins all of the work that we do for machine learning is with the feature store. So from the start of the development of a model, our data scientists, machine learning engineers define and iterate on new features. They're going to load new features for model training and then load features for model testing, and that's the model development cycle that you see there at the top, on the top left. And then in inference, we're going to compute feature values for inference. So we want to make predictions with our models. We want to log the features that are used in inference. We want to track some statistics about our features to look for things like feature drift, where maybe features change under time because of something underlying the way the a change in the business or something that changes underlying data. So this is just a hypothetical, but you could imagine, what if you're a bank and you only have checking accounts and you have a feature that monitors account balance, and then all of a sudden you add the ability to get savings accounts and people start to move money into savings accounts, you're going to see some big shift in the checking account balance. So you want to be able to monitor that, which our feature store through Tekton provides some amount of functionality for us to do, assisted by internal tooling as well. And I guess that also goes hand in hand with monitoring for drift and quality issues at the end there. So every point of the model development and production lifecycle depends on this feature store. And without it, we wouldn't be able to do what we do in machine learning. Okay, so that really concludes talking about how we use the feature store for our machine learning. We have a secondary thing that we want to share about as well, to where our feature store has taken on somewhat of a new life beyond just the machine learning applications. So this roadblock that we had as a company was other teams we were discovering were needing real-time metrics, and really what are machine learning features in some sense besides metrics. I mean, there's a very real possibility we're just talking about the same thing in other names depending on who's developing these things. So as we talked to other teams in the company, we found out that, for example, other teams were building rules engines that were not running machine learning models per se, but these essentially expert rules engines that were being used to make decisions in the life cycle of the company. So an example is lending risk. There were lending efforts outside of just the machine learning efforts, where we have several lending products, and they use these rules engines to decide if someone is qualified for a lending product. Similarly, we have fraud detection that we'll talk about more here, where a rules engine is being used to just look for obvious, maybe not obvious, but fraud that can be detected without some sort of advanced machine learning approach. Similarly, even in our customer-facing app, there's certain data. We have a very data-rich app that we want to make as useful for our customers as possible. Our bank is a modern bank doesn't have bank branches that you go into, and the app is really the bank branch for our customers, where they get the information, communicate with us, and do everything they need to do. And there was a need for metrics that were complex values computed off data that was only available through the data lake, essentially, to be communicated with customers. And what we started to realize was that the online feature store, which is just an ability to serve metrics, essentially, keyed on something like a customer ID, was going to be able to serve this data as well. So to just jump into one of those examples, this is the lending risk rules. So a year or two ago, we implemented Zelle, which is American bank-to-bank or customer-to-customer transaction that works between banks. So you can send money to a friend. And in the implementation of Zelle, we used a tool called Slide Rule, which is a lending risk rules engine tool to perform a decision as to whether we should allow a Zelle transaction to go through. And so each transaction would send a query through this rules engine and look for a result back. So that rules engine has a need for data, right? So they're trying to make a decision about this customer, about this transaction. Is this going to be a valid transaction or a fraudulent transaction? Is this a decision? Sorry, I said this is a lending example. This is a fraud example, not a lending example. Is this transaction at risk of being fraud? Is the decision that we needed to make. And so the conclusion that we came to as a team was that these business metrics used in this type of decisioning process are really machine learning features. And so became an ability to reuse this feature data as metrics to feed this rules engine. So what we developed on top of Tecton was a gRPC interface to the Tecton online feature store so that internal services could make these gRPC calls to query up-to-date real-time data for our other services from our feature store. So again, the data comes in from data streams, Kafka, from the data lake, and then features defined in SQL are materialized in Spark. And then the Tecton online store writes that updated feature data into a DynamoDB database, which is essentially a fancy key value store. And then the Tecton API that's provided to us provides REST access to that data. And then we've put on top of that a gRPC API to match with how our internal services are built to be able to query that data. So going back to our example of a Zelle transaction, the information of that transaction hits this slide rule rules engine, and then that rules engine over gRPC is able to say, hey, here's the customer's ID. Give me the most up-to-date data that you have about this customer that's relevant to this Zelle risk decisioning process. So as that data is returned, they can then within milliseconds make the decision that they want, and then push that back, and then decide the system decides whether or not this Zelle transaction is able to go through. So what's remarkable here is that we were able to construct this in such a way that we basically didn't have to build new infrastructure other than this gRPC interface, which we would have needed otherwise, to solve this problem internally. So simply by taking advantage of what was already in place, we were able to get a whole breadth of applications out of our online feature store as well. So that's part one here. Online feature service architecture is reusable with minimal additions. Then the secondary benefit is that this cross-pollinates the metrics and features across teams. So all of this data for us lives in a unified, what Tecton calls a workspace. So that all this data, whether the data scientist defining machine learning features or banking analysts or engineers defining data for other applications, all of that lives in one place within Tecton, and then that data that a lending analyst develop maybe is going to go into a machine learning model in the future, because the data scientist can go in, look at that data, and decide on its potential value for a machine learning application. I say one of the biggest challenges that we faced here is that this just requires some amount of diligence for us to ensure quality data, as we have opened up the door for engineers, data scientists, analysts to write features. And sometimes those can be fairly complex features and things with domain knowledge that me without a banking background doesn't necessarily know how to evaluate. We've had to come up with policies and procedures for reviewing those, having multiple people review those definitions, as well as doing data validation, and then also helping non-machine learning folks understand just some of the constraints that we have in place to make sure that we're not introducing data leakage into machine learning models by introducing data into the system that appears to have been available prior to when it would have actually been available. So the common problem in machine learning is training a model to predict something with data that you wouldn't have known at the time of prediction. And Tecton has a lot set up that enables that to be as straightforward as possible. There's still kind of the ability to shoot yourself in the foot there and push data in incorrectly. So even when data is not intended for machine learning use cases, we've had to work with folks to make sure that the data is viable for machine learning use cases. But all in all, this has been extremely beneficial for us, both as a machine learning team, for our data science team, in enabling faster, better, more reliable model development, but then also use cases beyond that, as I've shared other teams using this gRPC interface to access that same data in real time. All right, I'll stop there. I'm happy to take on questions as people have them. I can hang around as long as people need.
Thank you so much, Tim. That was excellent. We do have quite a few questions that came in from the audience here, so I'll start relaying those to you. Let's see. First one that came in was, in the context of batch data, which technology is used above the data lake?
Above the data lake?
Yeah, I think this came from earlier in your presentation. You were showing a diagram.
So I'm not exactly sure what that means, but our data lake is all built on AWS data lake and AWS Glue. So it's all Spark jobs and AWS Athena jobs for us. If cool. That doesn't answer the question, feel free to clarify, whoever asked that.
Sounds good. The next question was, how does Varo handle the challenge of feature ownership? In other words, ensuring that the pipeline is healthy, online features stay fresh, etc. Does the ML platform team oversee all features, or do individual teams own features like they might own models?
Yeah, that's an extremely good question. Someone who obviously knows what they're asking. This is still kind of a developing thing for us. We rely heavily on a couple things that are components of Tecton that are very valuable. Tecton has fairly basic but very powerful data monitoring things. So you can define, for example, for a real-time, for an online feature, you can define this data should be at least this fresh within, for us, it's often a day or 2 days. And then we get alerts for those if that data is not fresh. There's other types of alerting that Tecton can offer. For example, if a feature is normally not always null, and then one day all the features are null or all zero or something like that, it could be an alert that there's something going on with the upstream data. So we typically handle that through our machine learning platform team. Specifically, we have an on-call rotation, and so the on-call person is the first one to triage that. But then Tecton also allows you to tag different features with a feature owner. So we do ask the people who write the features to be tagged as the feature owner. And so we often have one of two things as we start to look into it. We can either go to the feature owner and try to investigate with them as to what might be going on, or if we think it might be a data issue, we raise it with our data engineering team on-call person and find out if there's some kind of upstream data. So I guess to summarize, our machine learning platform team becomes the first level there, but that might be something we raise with the feature owner or feature creator as well.
Cool. That's great. I think this question might be similar in nature, but I'll ask it anyway. You touched on non-ML consumers of these features, for example, the business analytics, backend rules engines. Did you experience any friction in handing off these features to non-ML customers, and how did you address that?
Sure, yeah, a good question. There's sometimes can be friction around, for example, just understanding something as simple as maybe the schema of the data, or how the data is, maybe the format of the data. There can also be a lack of understanding sometimes by our consumers as to the whole data lifecycle that we talked about here. And so, for example, if sometimes this online data is relying on underlying batch data sources, there might be a larger delay in getting access to that data than they're expecting, and that's often just a misunderstanding of the process. There, I think, have also been cases of data being defined incorrectly, and so they're actually getting data that's not the data they should be getting. We're small enough as a company that most of those are just handled in a very personal and ad hoc basis as we deal with those things. We don't, yeah, I mean, you can just find somebody and go talk to them is really the short answer to how we handle that. At the same time, we try to deal with that proactively by just better documentation and communication about what we're doing and what we're making available, as well as being really proactive as a team to just reduce mistakes and bugs on our part, as well as helping prevent feature authors from introducing bugs into their feature definitions. So we're kind of always iterating on our validation process to make that better and better, to try to catch any potential data issues before they happen, because those can obviously cause real production challenges.
Awesome. The next question is, can you speak to the scalability and latency of feature engineering platform, such as the rough number of ML features, number of entities, entity types, QPS, and the latency of updating a feature, so new events coming in to updated feature value? Any ballpark of those benchmark statistics?
Yeah, I'm not great off the top of my head about the latency and QPS and various things that Tecton provides SLAs for. I would point you to the Tecton documentation, which is really good, and I'm sure has that information, and tends to be very reliable for us. We have around 1,200 features in our feature store, and so Tecton has a concept of a feature view where features are aggregated together based on, do these features come with from the same query? So we don't have 1,200 feature views in the Tecton sense, but we have around 1,200 features. And with entities, we try to keep our entities count as small as possible. Often there can be different ways. So in a bank, for example, there might be multiple IDs that might point to a customer based on different point in the customer's life cycle, as well as you can think about an account for a customer. our customers typically have a checking and a savings account. But we have tried to, as much as reasonably possible, standardize on, okay, use this customer ID as the standard ID. And then if you need to map that to something else in your model or in your end use case, do that. But trying to make that as widely used as possible, which hopefully simplifies things in the long run. Yeah, I'm sorry I don't have better numbers on the latency and those type of values, but usually we can get things as fast as we need them.
That's good. That's what matters.
Yeah.
The next question is, what metrics or benchmarks do you use to measure feature quality?
Yeah, this is a hard one. This is one that I think about laying in bed at night, because I think it's pretty hard to quantify in absolute terms. We have an internally written a feature style guideline, which not only defines some just basic standards of, for example, here's how you name your features, but also just tries to provide some guidance into construction of features around things like don't do unnecessarily like idiomatic or complex transformations to your data that could be done just within the model itself. So maybe you need your data scaled by some factor, but it only matters for one particular model. How about you instead define that feature more generically and then to scale it in the model itself? Something to that effect. And there are other things that we're continuing to develop, but it's hard to really think about like kind of absolutely defining a metric that can be used, because every feature that someone's creating is different. One of the things that we also really emphasize is Tekton has a very powerful aggregation system built into it, which allows you to just think about your features as defining basically individual events that occur, and then Tekton will do the aggregation for you. So instead of thinking about calculating your customer's account balance standard deviation, if you can just give Tekton the account balance from each day, you can then aggregate, have Tekton at retrieval time do that aggregation for you. So we try to push our end users as much as possible to use those Tekton aggregations, which helps just simplify the actual definition of the query itself. And simpler queries are easier to review, easier to have confidence in, less likely to have bugs. So that's a good thing, but sometimes just the nature of what needs to be done ends up being more complicated queries.
Understandably, a pretty complex thing to figure out. So I'm going to move on to the next question here. It's kind of a two-part question. Is a packaged solution used to link streaming and batch data, or was it developed by a systems department? If developed, is the solution, for example, FIS or Jack Henry, used to in the core banking solution?
I'm not familiar with what those tools are, but the unification for us comes predominantly through what Tekton provides for us, where Tekton's able to mount data sources, both batch and streaming data sources, and then you're able to define your deserialization for your streaming data sources, and then write SQL or PySpark commands against either batch or streaming data sources. So Tekton basically solves that problem for us on the whole, which is really nice. It would be a very hard thing for someone to implement at a small-ish company without a lot of specialized ability. So yeah, if there's a follow-up to that, I'm happy to answer it. But
cool. This is similar. I think you said there's about 1,200 features in use at Varo, but this question I think is referring to the overall volume of data. It says, what order of magnitude is the size of your data you are using for ML models, source data, and the smaller feature store? Have you encountered any performance degradation as you grow in size?
Yeah, so I mean, we're often thinking about like training data on millions of entities often, although that varies depending on the type of model. I don't think we've really experienced performance degradation as we've grown in size. Sometimes we've experienced, we've worked with Tekton because our not as our customer base has grown, but just as the complexity and the number of features that data scientists and others want to use grows, we can put strain on what Tekton is able to do. And I mean, at some point, you'd put strain on any type of system where you're just trying to make that more complex, and you're in the background having to pull down a huge amount of data and do a bunch of joins on it. And so there's some amount of art, again, both for Tekton or would be for any type of system, to kind of understanding the limits, but then also sometimes just learning how to construct your feature definitions and other things in such a way that are going to be easier to compute. But yeah, the size hasn't particularly been an issue for us.
That's great. Another really great feature sharing reuse question, I think. What strategies did Varo's ML platform team use to encourage feature reuse, especially when teams left to themselves might optimize solely for transformations that they plus their models need?
Yeah, I mean, again, I think a lot of that for us is just handled through just the conversations that we have and working with folks who are developing new features. So someone from my team, every time a new feature is created, like someone from my team is looking over that, looking at the data, trying to understand the business use case, and then trying to understand how that is going to fit into the feature store in the long term. And so, we're able to sometimes work with the feature creators and say, you did it this way. If we did it this way, would that also work for you? Or can you think about this, which would make these features more useful to a machine learning model in the future? So yeah, if someone knows how to like automate this and really scale it out, I'd be super interested, because it's a huge part of my job, and I think there is a lot of it that's just, it's more of an art than a science, and that art can be hard to just codify and automate. But yeah, I would love to talk to anyone who's come up with better procedures there.
More of an art than a science is a great way to put it. I didn't catch this question because it was in the chat section, but it's a little different. Do you handle microtransactions using blockchain and serve as a clearinghouse for financial clearing? I'm not sure.
I think the answer is I don't think so, but I don't totally understand what all that means. So, but probably not.
Yeah, I can't help there either. I am not a blockchain or financial services expert. But that is all of the audience questions that came in. This has been amazing. Just been rapid fire questions at you, Tim. So
sure.
Thank you for the awesome presentation and for this really insightful Q&A. We really appreciate your time, and thank you so much.
Absolutely, and people can feel free to get in touch with me if they have more questions. I'll do my best to answer them, and as I hope I've shown, I'm happy to say I don't know if that's the answer. So
Cool. All right. Well, thank you all for
thanks,
joining,
Julia.
and hope to see you at the next one.